Okay, so hello everybody. So I will present the MASSALYA platform today. So it features and some application that we carried out on ecosystem studies this recent years. So this is a nice pictures of the platform at home, Marseille, in front of the major cathedral. So this platform is located at Marseille, France, and is associated to the chemistry and environmental laboratory at Aix-Marseille University, which has a strong know-how in atmospheric chemistry. So it's we are like 6 researchers and 5 technical supports. So I'm in charge of the MASSALYA platform. So it offers state-of-art and in some cases unique equipment, instruments, and expertise to support academic research, thanks to public funding and competitive grants. So the platform is open to collaboration with public research teams and provides easy access to technical information about the instruments. So this platform is gathering a set of instruments for the analysis of pollutants in the gas and in the particle phase. So state-of-art means that it provides real-time monitoring at ultra-low detection limits down to the ppt, and with very rapid response times down to 1 second. The most advanced equipment are using the mass spectrometry time-of-flight technology. So this allows to carry out non-target analysis most of the time. So one of the key instruments of the platform is PTR-ToF-MS, proton transfer reaction mass spectrometer. So it's this instrument, it has been widely used in many fields, as you can detect in real time and at once a range of VOCs at trace levels with a very fast response time. So for those who are not familiar with the technology, it uses a hollow cathode that you can see on the left to produce H3O plus ions from water vapor. And in the drift tube, the gray cylinder here, so you can have interaction between these H3O plus ions and the VOCs that are sampled from here and coming from the ambient air. So this VOC can react with the H3O plus and get protonated. So what is very attractive for this method, that a lot of VOCs are can be protonated. So as you can see on the right graph, this means that all the compounds which have a proton affinity higher than that of water can be protonated. So it includes a lot of biogenic species that are shown on the with the green arrow, and it includes a lot of biogenic species and also its oxidation products. You can also detect compounds which are which cannot get protonated if you use other reagent ions such as O2+, and in this case you can extend the detection capabilities to halogenated hydrocarbons, for example. Also, one of the benefits of the PTR-MS is that it's very soft ionization technique. So as you can see on the left graph, we compare the mass spectra of acetone and isoprene in PTR-MS in blue, and in red with electronic impact. So we can see that with the proton transfer, you have much less fragmentation, and in most cases, the protonated ion is the main ion, as you can see on the right graph for compound with oxygen atoms. For the particle phase, we have an aerosol mass spectrometer. So it allows to monitor in real time inorganic species, including sulfates, nitrates, ammonium, and chloride, in addition to the organics. And you can also get the size distribution of these 5 components. If you add an ethylometer to measure black carbon, you can get a fairly complete picture of the particle composition, of the particle chemical composition. And we can also associate a scanning mobility particle sizer to analyze the particle number distribution in the air. And more recently, we have a new instrument which is a Charon PTR-MS. So actually, it's a counterpart of the PTR-MS, and it's associated with an inlet, which is shown here, and that allows to sample particle. So first, you have a gas phase denuder that will remove the VOCs, and the particles are concentrated and evaporated so that the vapor can be detected by usual proton transfer ionization. So the advantage of this technique is that it allows to get a very clean mass spectra. So you have like here 5 mass spectra different from different markers of particle in the air. So including methoxyphenols and anhydrous sugar and also linear acids. So you can see again that in most cases the protonated ion is really the main compound, and this can give you a hint for the later identification of the organic composition. When these instruments sample air simultaneously, their data sets can be combined to answer key questions on the main sources, anthropic and biogenic, driving their atmospheric concentration levels, on their oxidation states, and also the age after they have been emitted in the air. And therefore, you can evaluate their impact on air quality and Earth climate. So all these instruments can be hosted in a truck that you can see on this picture. And we have also, this truck was designed for in situ measurements, of course, with air conditioning and roof openings that let us sample outside air in the best possible way. We usually also associate a weather station to measure the wind direction and wind speed, in addition to temperature and humidity, so that you can, once you combine the data sets, the time series of the atmospheric pollutants and the wind speed and the wind direction, you can get pollution roses that are shown here on the right. So this is an example of a campaign we carried out on the port of Marseille, and this illustrates the origin of the particles. So you can see on the radial axis you have the wind speed. Sorry. So you can see and the color scale indicates the particle concentration. So from blue to red in increasing order. So you can see here that most of the particle high concentrations are associated to the enters of the port on the north and the south side. So this combination of state-of-the-art instruments that can be fitted in a truck has offered many collaboration with academic and non-academic partners in France, but also in many countries in Europe and US, and also for lab experiments. So now I will switch to some applications that we have carried out in chemical ecology. Many of them were done with Elena Armeno from the IMBE. So let's go. So the first of the, one recent application that we did with the PTR-MS was used for the emission of Posidonia oceanica, which is the most abundant Mediterranean seagrass species, which cover more than 12,000 square kilometers. So even though seagrass covers large area over the coast, they haven't been used much as source of VOCs, and they can affect things like ozone and aerosol formation in the atmosphere. So in this lab study, we have 5 individuals of Posidonia oceanica, which were collected just one day before they were brought to the lab. And so the idea was to measure online their emission, so the headspace emissions from the 6 dynamic chambers. So these chambers were filled with seawater recreated to reach a salinity level typical of Mediterranean Sea. And we can, thanks to the PTR-MS online measurements, switch between the 6 positions to analyze online the diurnal cycles and identify the VOC emission from this seagrass. So what we could detect is that we have very different compound families, including sulfur compounds, oxygenated compounds, aromatic compounds. and their emission were comparable to what have been measured from land plants. And most compounds show, so it's here, sorry. Most compounds show clear diurnal cycles, as we can see on the right graph here, for example of acetone. But for DMS, surprisingly, this was not the case. So again, this is an application of what can be done in lab experiments to identify and follow online with a very high time resolution the emission of a ecologic system. So because the PTR can provide also non-target analysis of VOCs at trace levels, it has been associated to many studies carried out at one of the AnaEE-ERIC facilities, the O3HP, Oak Observatory at the OHP, in the south of France, to monitor the dynamics of BVOC emissions from plant and soils. So the site is equipped with a roof, with a precipitation exclusion system to simulate a drier climate based on prediction from for the end of the century. So basically the roof here open and close remotely on demand, and mainly from late springs to late fall during about 20 days a year. And the canopy is accessible to through a scaffolding in form of a cross under this. In these experiments, we did some experiments. So at the branch scale, which were enclosed in Teflon frames and flushed with air in order to follow online the rapid diurnal variation of BVOC emission rates. So actually the setup. So you can see the scheme of the site with the roof for the exclusion, and the scaffolding to access the two different plots. So the plot which is supposed to simulate the natural drought condition, and the plot under the roof, which is used to simulate the amplified drought of the forest. So the approach was to sample in parallel one of each plot, 1 or 2 days, by switching with a valve every 20 minutes between the two dynamic branches, and then to shift the setup to another pair after 1 or 2 days of measurements. So this is so you have two graphs on the right where we just show the diurnal cycles over the 3 different seasons that we carried out the measurement, spring, summer, and fall, for the natural drought and the amplified drought. So on the bottom graph for isoprene, we can see that we can see that we have clear daytime variations, and that really follows the light temperature dependence algorithm. But still, for some compounds, so for example for methanol, this is the top graph on the right. We also saw some nighttime emissions and early morning bursts that is really clear in the spring season here. That were not modeled by the algorithm, of course. So these bursts were associated to a strong release of these components that had been accumulated over the night, and were released when the stomata just opened at dawn. So overall, this result confirms that seasonality and drought are parameters that need to be considered to improve the models that predict BVOC emissions according to the type of vegetation, biomass, and leaf age. The same approach was carried out in another study to study the litter emissions of the trees, so the Quercus pubescens. So the same approach, switching between a litter which was under the amplified drought and natural drought, and switching to another pair of litters for after 1 or 2 days of measurements. So first, what we clearly saw that the litter composition was very different from the leaf emission composition. For the litter, you have the most components were acetone and acetaldehyde, while for the plant, for the branch, it was isoprene, which was the main component emitted by the trees. And also, we also saw that we have a 200-fold difference between the litter and the trees being the main emitters. In addition, the real-time measurement over the few days show that there is a clear diurnal cycle also, as we can see, as we observe for the plants. And the temperature was the main driver of BVOC emissions, regardless of the drought condition. And as a model diurnal cycle, here in black, here follows the measured one in blue. This was especially the case for monoterpenes, acrolein, acetic acid, hexanol, and the sum of VOCs. However, for some specific compounds, such like isoprene, we saw that the litter acted as a sink instead of a source of VOCs. And comparing the plot with amplified versus non-amplified drought, we could see that we had a decrease of 43 or 40% roughly between the natural drought and the amplified drought. And the decrease of BVOC emission from the amplified drought can be related to lower soil microorganism activity and thus slower litter decomposition under the long-term rain exclusion, as indicated by the reduction in soil respiration and the positive correlation between the BVOC emission and the soil respiration. We also carried out additional studies on the litter emission, and the approach was different. It was rather a VOC screening of the different litters that are available in Marseille. So we choose to study the 15 most abundant deciduous tree species in the city of Marseille that covers within the city limits like 600 hectares of urban green spaces. So in the context of the development of green spaces in urban areas to fight against heat island, polythought vegetation could lead to deterioration of in-air quality. So to minimize constraints linked to secondary pollutants, such as ozone and secondary organic formation, it's important to select the plant species that emit minimal VOC. So these box plots summarize what we found. So we have first huge variation in the emission factors, as they span like 3 orders of magnitude. And there is also large variability in the number of VOCs which are emitted by the specific species. From 3 to 60 distinct VOCs were identified. And also, if you consider the impact of these VOC emissions on the quality in their fate in the atmosphere after they have been emitted, what we saw is that they have also large variation on the potential ozone formation and SOA formation. As again, we have in ozone potential formation, it spans over like 100 order and 1,000 orders of magnitude for the ozone and SOA formation, respectively. Okay, so we can also study the impact of the BVOC emissions in the lab, and we try to mimic what happens in the atmosphere in fast conditions. So for this kind of studies, we can use an oxidation flow reactor. It's a type of continuous flow, so it's shown on the left, sorry. So it's a kind of flow reactor that uses very high oxidant levels in very well-controlled conditions to mimic atmospheric oxidation chemistry that happens in days to week scale. So you can see on the left, so the picture of the flow reactor when the lights are on. And on the right, the whole setup for the experiments. So in this application, the litter here is continuously flushed and the emissions are pulled in the flow reactor where they are left to react and as they flow to the outlet. And at the outlet, you can monitor the products of the reaction, both in the particle and the gas phase using a scanning mobility particle sizer that we saw before, and the PTR-Charon. So PTR-Charon to alternate between the VOC measurement and the particle measurement. So we choose to do this experiment with Pinus halepensis. So why this plant? So it's because it's the most widely distributed pine species in the Mediterranean region. It covers 3.5 million of hectares. And also it's a very strong litter producer. And in addition, when you take a look at the BVOC composition, you see that most of the VOC emitted are monoterpenes and sesquiterpenes, which are known to yield SOA in very high levels. So this is an example of the result that you can get with this kind of flow reactor. So you have on the top graph in green the monoterpenes emissions from the litter. In black, this is the particle concentration in mass. And on the bottom graph, you have the size distribution as a function of time. So again, on the y-axis, this is the size of the particles, and the color code goes from the blue to the red in increasing number concentration. So what we can see, if you go back to the top graph, is that the monoterpene levels drops suddenly as soon as you turn the lights on. And it's combined with also sudden increase in particle formation. So it really shows the potential of aerosol formation from the volatile organic compounds reaction in the air. And so we had the opportunity to try to use the Charon mode to investigate the organic composition of the particles which are formed. So again, if you remember, with the Charon PTR-MS, you have a very soft ionization, so you can get a very nice picture of the molecular scale of the organic composition. And we also tried another ionization mode, which is a mode with ammonia. Ammonia to extend the range of compound that we can detect with the PTR method. And the results, I mean, some of the results are shown here on the right. When you compare the particle mass composition and the organic composition with the NH3 and H2O+4 ionization mode, and you can see that with the NH4+ mode, which is on the top graph, we were able to detect compounds with oxygen atoms up to 5 to 6 units. So this kind of study can also help to investigate the chemicals and the chemistry leading to particle formation. Okay, so these were like a few examples of what the platform can do to study ecosystems. I will end up with my presentation with this nice picture. So feel free to ask questions if you have some.
Yeah, super. Thank you very much, Bryce. It's really interesting. And it's nice to learn a little bit about a technology that we can have hopefully in more of our AnaE sites and facilities. Yeah, so I will start off. I can see that Stanislav, sorry if I pronounced your name wrong, you were first to raise your hand if you want to.
Good morning. Thank you very nice for this pretty impressive talk. It's very nice, your instrumentation. I have also a question. I see this mobile lab. Is it possible to measure while you are moving, let's say driving a street? Because I was wondering how you are dealing with running so lot of instruments in parallel for the energy consumption. Or you just move to the spot and there you switch everything on?
Yeah, this is what we do. This is what we do. We don't measure while driving. I know it's possible. We have some lab who have this kind of possibilities, but we don't.
Yeah, because it would be maybe pretty challenging to have everything on.
Yeah, also challenging is for the power, but also I think for the vibrations of the instruments, because you know it's mass spectrometers, so they are still pretty fragile instruments.
Yeah, that's true. Okay, thank you.
can see that Nicolas has a question now. So I'll let...
Yes, thank you for the nice presentation. Just a question, a general question. How much did you observe, how much environmental variation did you observe in terms of times, for example, from day to day, from time to time of measurement, and from other external factors? How much was this variation?
I'm not sure to understand variation of which emissions, or
in the VOC, for example, from Venus or from another situation.
you mean the variability of the emissions?
Variability, yes.
I think it will depend on many parameters, but you can observe between like some PPT levels up to PPB levels. It will depend on...
No, experimental variation. Which is the extent of the experimental variation that you observed?
Sorry, I can understand. Which variation, which experiments?
I mean, you make measurements in one day and then you come back in another day of the next week, and which is
No, the experiments they are done in a row.
It's continuous
yeah,
recording.
Yeah, it's continuous recording over a period between 1
and
week
which is the
and 1 month.
fluctuation? Okay, what is the fluctuation within 1 month or?
Of, like, for example, isoprene, you mean? For isoprene emissions, you mean?
Maybe related to uncertainty, no?
The uncertainty on the experimental conditions. I mean, there is some uncertainty which depends on the emission, but I think everything is normalized to the. I mean, if you consider the plant emissions, actually, I'm not sure to be able to answer to this question. We should go back to the paper to see that. But I think, yeah.
So in some cases, I saw that there was a bigger variation. In other cases, a smaller one. It's okay.
Yeah.
Yeah, I think it was nice that you mentioned that you have some pre-existing papers, and maybe that would be really nice to share with this group, and that might answer some of the questions that people are having.
Yeah, sure.
Yeah. But we'll move on to Joseph's question now, if that's all right with Nicola.
Can you hear me okay?
Okay.
Yeah. Yeah, I think I have quite a few questions, but I probably start with the first one. Bryce, I'm not sure if you're how much you're familiar with the ERIC concept and research infrastructure, but basically my question is that given AnaE perspective, where do you think mobile laboratories could fit the best, and basically what would be the most kind of efficient way to use them within ERIC framework?
I think we can. So I'm not aware of all the ERIC facilities, but I think for the MASSALYA point of view, you can make in situ measurements, and you can also deploy the instrument in the lab. So we can either do in situ measurements or do like reactor or dynamic chamber scooping. So these are the two main experiment that we usually carry out. Also, in terms of time, usually, okay, we do some project and we stay like 1 week or 2 weeks or 3 weeks on the same place to do the measurements. So we also need to optimize the experiment to be able to do that in this period of time, because the platform is kind of very busy. So yeah.
Thank you.
Yeah, I can see before I move on to Klaus's question, I can see that Michelle has asked a question in the chat which kind of links to Joseph's question, and it's just relating to how far the vehicle can drive from Marseille. Because I think if we know that, then we can kind of have an idea of how many of our other facilities could benefit from this service.
Yeah, we've been up to, to Finland, to Germany, Spain, Italy, Swiss, even we went to Fairbanks, Alaska. So we are rather flexible and mobile. Yeah.
Yeah. So that's promising. Klaus has his question now, but he's unable to turn his microphone off mute. I can see on the icon that it looks like it's been disabled. So Klaus, if you want to write it in the chat. Yeah, and then we'll move on to the next question, which is, I'm not sure if it's Stanislav Duran
yes,
or if it's
me.
Duran Stanislav. Yes.
Stanislav, yeah.
Yeah, okay. Thank you.
I have a question about the seagrass experiments. Please, can you a little bit advise me what is the best for the chamber measurements? What is the best material for the chambers? Is it Duran glass or is it a kind of transparent Teflon or?
I think it's so this experiment we are done in collaboration with EMBE, like ecological laboratory in Marseille, with Elena Ormeno, and if I remember well, these were glass chamber covered with a Teflon cap. But this can be also confirmed. I think this was also published in 2025, so you can get all the details of the experiment in the paper.
Yeah, I put a note about the paper. Okay, thank you.
Okay.
And yeah, Klaus, you can ask.
Can I go now? My mic is enabled. Thanks. Yeah, thanks a lot for this interesting presentation. And I really think in general that the mobile systems has a great potential in AnaE. We just need to learn better how we can make even more use of them. And I think you already commented a little bit on Joseph's question, because my question was related to how long are you normally visiting another site, because that might give people a better idea of what options are there. And I would like to hear about your experience about going to one site for just 1 week and doing something really nice that you can actually use in a publication. So maybe my question is, how long are you in general when you go to visit other groups? How long are you there? And if you could give some examples of how you work intensively in a short period of time, and that leads to a nice collaboration and paper.
I think usually we do like 2, 3, 4 weeks on the site. Okay. I think you need it depends also if the setup is already ready and running. Sometimes you need to make some adaptation on the setup to allow the coupling with the analyzers. So usually you need to plan like 1 week in preparation before doing the measurement. So if we plan a 3 weeks experiment, I think we need to add another week before to install everything and be ready. Usually we try to, because all these are also mass spectrometers, so they don't like to be at atmospheric pressure. So what we do usually, we try to leave early in the morning and drive, and to be able to restart the instrument in the evening when we arrive. So this is the best case, or even 2 days if we really need to travel far away from Marseille.
Okay, thanks.
Thank you. I have 2 questions from Joseph that are in the chat, so I'll just read them out. So the first question was, how did you choose which equipment to include on the platform?
So how did we choose? I think we try to. So first we first started with the aerosol mass spectrometer and the PTR-MS. At the time it was a quadruple mass spectrometer with the PTR, and we try to follow the evolution of the technologies. So then we could buy a time of flight mass spectrometer. Then the next instrument, I think it will be more like a SIMS instrument, so to extend the range of compound that you can measure. So we try to keep the platform attractive for collaboration. So by having kind of the state-of-art instruments for I mean, and to extend the range of application. Yeah, and the analytical capabilities of the platform.
Super, thank you. There's one more question in the chat from Joseph, and then we'll move on to Nadia's question. But the question from Joseph is, what fraction of the year is the platform in use? So how busy is it? How available is it for other users to kind of work with?
So I think every year, I think we have like 150 days of measurements. Yeah, like this. So we also need to have some time for the maintenance. Yeah.
Is that seasonal? So is it normally more busy in the summer when there's more VOCs happening, or is it?
The fact is that the platform is not doing only ecosystem studies. We also do like anthropic measurements, like in urban areas, or some lab experiments also. So usually the platform doesn't work in August because it's vacation in Marseille, but we can also adapt. We can also adapt this kind of stuff. So we are quite flexible for the timetable.
Yeah.
Most of the time also, you know, the platform, it is associated at the stage when the project is being built. So to associate also the researchers, we have also some Julien Kammer also at the lab, who works also on biogenic emissions in collaboration with Elena. So we try also to associate a researcher. This is not always the case, but it's also possible.
Nice. Yeah. Well, I think that was a really interesting session. I think there's some great questions, and it was a great presentation from you, Bryce. So I think it's a good time to say goodbye and have a lovely weekend. Thank you everyone for joining, and we'll see you at the next TechUp session.
Okay, thanks for listening.
Thank you so much.
Thank you.
Thank you. Bye.
Thank you.
Thank you. Bye-bye.
Bye-bye.
Thank you.